everyone, nice to see you here. In this video, I'm going to talk about the powers and roots of complex numbers. In my previous video, we have learned how to change complex numbers from Cartesian form to polar form. If you haven't watched it, I suggest you watch that video first, then come back to this video. If this is your first time here, and if you want to improve your math skills, make sure you subscribe my channel by hitting the subscribe button below so that you won't miss any videos later. If you find that this video is useful, please share to your friends, to your students, or to anybody who need this. So, let's start the lesson right now. In this video, I'm going to talk about powers and roots of complex numbers using the Moivre's theorem. If we want to find the power of a complex number, for example, z to the power of 2 or z to the power of 3, we can use binomial expansion. However, if we want to find z to the power of 10, z to the power of 12, the binomial expansion is not practical because the working step is complicated and takes time. So in this case, we can use the Moivre's theorem. So before we can use the Moivre's theorem, we must change the complex number into polar form, that is r cos theta plus I sin theta. Then first we separate the power. Then under the Moivre's theorem, cos theta plus I sin theta power n is equal to cos n times theta plus I sin n times theta. Now let's look at this example. Now I want to find the complex number 1 plus I power 12. So first I need to change this complex number into polar form. So first I am going to find the modulus by using the formula square root of x power 2 plus y power 2. X is 1, y is 1, so the modulus is square root of 2. As for argument, since the complex number is in the first quadrant, so the argument is arctangent y over x. With the value of y is 1, x is 1, so the argument is pi over 4. So now I have changed the complex number into polar form. So first I separate the power. Then for modulus square root of 2 power 12, it is equal to 64. Now as for cos pi over 4 plus I sin pi over 4 power 12. Under the Moivre's theorem, the argument becomes 12 times pi over 4. It is equal to 3 pi. So after this, I need to change the complex number back into Cartesian form. Now I press calculator for cos 3 pi, I will get negative 1. And sin 3 pi, it is equal to 0. So therefore, the answer is negative 64. Now we go to n roots of complex numbers. If we want to find n root of a complex number by using the Moivre's theorem, so first we need to change the complex number in polar form. Then we separate the power. Under the Moivre's theorem, cos theta plus I sin theta power 1 over n, the argument becomes theta plus 2k pi over n, where k is equal to 0, 1, 2 until n minus 1. So from here, we notice that the answer is more than 1. It depends on the value of n, where square root of z, we will get 2 values. Cube root of z, we will get 3 values. Fourth root of z, we will get 4 values, and so on. Now I'm going to discuss in detail about this. Under the Moivre's theorem, cos theta plus I sine theta power 1 over n is equal to cos 1 over n times theta plus I sine 1 over n times theta. That is cos theta over n plus I sine theta over n, where the value of k is equal to 0. So this value is considered as the first root of the complex number with the argument theta over n. And we know that the number of root depends on the value of n. All the n value will distribute equally along the circumference of the circle here. So for example, when n is equal to 2, means there are 2 values of root. So first value of root is here, and second value of root is here, where the 2 values of root divide the circle into 2 parts. Then if n is equal to 3, so there are 3 values of root. The 3 values of root will divide the circle into 3 equal parts, where the angle of the center of each sector is equal to 2 pi divided by 3, where the second value will be somewhere here, third value will be somewhere here. When n is equal to 4, means there are 4 values of root, and the 4 values will divide the whole circle into 4 equal parts, where the angle at the center of each part is equal to 2 pi divided by 4. So means the second value will be somewhere here, third value here, and fourth value will be found somewhere here. And when we continue, when n root, there are n values of root, and all the n values of root will divide the whole circle into n equal parts. And the angle at the center of each of the sector here is equal to 2 pi over n. So to find the second value of the root, we follow the direction anti-clockwise. So the second value of the root is this one. Then the argument of the second root is equal to theta over n plus 2 pi over n. So we will get the second root, that is, the argument is theta plus 2 pi over n. So we can see that in the second root, k is equal to 1. Then we continue to find the third root. So the argument of the third root is this one, where it is theta over n plus 2 pi over n, then plus another 2 pi over n. Then it becomes theta plus 2 times 2 pi over n, where the k is equal to 2 for the third value. Then we continue until to the last root, that is n minus 1. For the argument of n minus 1, it is theta plus 2 times n minus 1 pi divided by n. So here we can conclude that we can use this formula to find the n roots of a complex number under the Moivre's theorem. Now let's look at this example. Find the cube roots of 8. When we write 8 in Cartesian complex number, it is equal to 8 plus 0i. if we want to find the cube roots by using the Moivre's theorem, we must change the complex number into polar form. So the modulus is equal to 8. As for the argument, since the position of this complex number is at the positive real axis, so the argument is equal to 0. So the polar form for 8 is equal to 8 times cos 0 plus I sin 0. Now to find the cube root of 8, it is equal to modulus 8 power 1 over 3 times cos 0 plus I sin 0 power 1 over 3. 8 power 1 over 3 is equal to 2. Cos 0 plus I sin 0 power 1 over 3 is equal to cos 0 plus 2k pi over 3 plus I sin 0 plus 2k pi over 3, where k is equal to 0, 1, and 2. For the first value of cube root, that is k is equal to 0, so the cube root is equal to 2 cos 0 plus I sin 0, and when we press calculator, we will get 2. For the second root, when k it is equal to 1, so the argument becomes 0 plus 2 times 1 pi over 3, that is 2 pi over 3. So the answer we need to change back to Cartesian form, that is we need to press the calculator. So when we press the calculator, cos 2 pi over 3, it is negative 1 over 2. Sin 2 pi over 3, it is equal to square root of 3 over 2. So when we simplify, the answer is negative 1 plus square root of 3i. Then as for the third root, when k it is equal to 2, the argument is 0 plus 2 times 2 pi over 3, that is 4 pi over 3. So to change back to Cartesian form, cos 4 pi over 3, it is negative 1 over 2. Sin 4 pi over 3, it is negative square root of 3 over 2. So after simplifying, the third root is negative 1 minus square root of 3i. So therefore, the cube roots of 8 are 2, negative 1 plus square root of 3i, and negative 1 minus square root of 3i. Now in the first example and second example, a complex number z is given, and based on the z, we are asked to find z power n and z power 1 over n. Now we are going to do the reverse process where a complex number z power n is given. Based on z power n, if we want to find z, means we need to throw the power n to the right hand side, becomes power 1 over n. So means if we want to find z, we need to use the formula of root. And the other case, if it is given z power 1 over n, and using this complex number, if we want to find z, means we need to throw the power 1 over n to the right hand side, becomes power n. So if we want to find the z, we need to use the formula of n power. Now let's look at this example. It is given that an 8th root of a complex number z is 3 minus 2i. So when 8th root of a complex number z means z to the power of 1 over 8. Solve the equation. Solve the equation means we need to find the complex number z. So to find the complex number z, now we are going to throw the power 1 over 8 to the right hand side, becomes power 8. To find the complex number power 8, now we are going to use the De Moivre's theorem. So before using De Moivre's theorem, the complex number must be changed to polar form. So for modulus, since x is 3, y is -2, so when sub into the formula, the modulus is square root of 13. As for argument, since the complex number is in the fourth quadrant, so the argument is negative arctangent y over x. It is negative 0.588 radian. So now I change the complex number into polar form. So first I separate the power. For the modulus, square root of 13 power 8 is equal to 28561. So for the power of the complex number, under the Moivre's theorem, the argument is negative 0.588 times 8. It is equal to negative 4.704. So now I need to change the answer back into Cartesian form. So when I press the calculator, I find that the answer is negative 239.6 plus 28560i. Now let's look at this example. It is given that w power 4 plus 16i is equal to 0. Find the roots. Find the root means we are asked to find the value of w. Sometimes the question sounds like solve the equation. Solve the equation also means we are asked to find the value of w. So first we shift the 16i to the right hand side. Then we get w power 4 is equal to negative 16i. So in order to find the value of w, we shift the power 4 to the right hand side, becomes power 1 over 4. So means here we need to find the fourth root of negative 16i. So in order to find the root by using De Moivre's theorem, we need to change negative 16i into polar form. So for modulus, x is 0, y is negative 16, so modulus is 16. For argument, for negative 16i, the position of the complex number is at the negative imaginary axis. So the argument is negative pi over 2. So now I change the complex number into polar form. Then I separate the power. The modulus 16 power 1 over 4 is equal to 2. Now for the argument, negative pi over 2 under fourth root, it is equal to negative pi over 2 plus 2k pi divided by 4, where k is equal to 0, 1, 2, and 3. Now when k is equal to 0, so the argument is negative pi over 2 plus 0 over 4, that is negative pi over 8. Then we need to change the answer back into Cartesian form. So we press calculator. Now we get the answer in the Cartesian form for the first root. Then when k is equal to 1, then the argument is 3 pi over 8. And when we press calculator, the second root is this one. Then for k is equal to 2, the argument is 7 pi over 8. When I change to Cartesian form, that is this one. Then when k is equal to 3, then the argument is 11 pi over 8. And when I change to Cartesian form, the answer is this one. So therefore, the roots for this equation are this one. Now we are going to solve the polynomial equations with real coefficients where the root of these polynomials are in complex root. So if a polynomial in terms of x with real coefficients means the equation has no imaginary number. So when we substitute a complex number into the polynomial and we find that it is equal to 0, so we can make conclusion that x equals this complex number is a root. Then from here we can say that x minus a minus bi is a factor of this polynomial. Then if x is a complex number, a plus bi is a root of the polynomial, and if the polynomial is the polynomial with real coefficients, so means the conjugate x equals a minus bi is also the root of this polynomial. So therefore x minus a plus bi is also a factor of this polynomial. When we combine these two complex factors, then we will get a quadratic factor for this polynomial. Now let's try this example. Show that the complex number 2 plus I is a root of the polynomial. So first we substitute the complex number into the polynomial. Then we need to find the value of the polynomial after substitution. Here the expansion power of 3, we can use binomial expansion of power of 3 to do the expansion. So after the expansion, then we will get this one. Then when we simplify, then this is the expression. So from here, because I power 2 is equal to negative, I power 3 is I power 2 times I, so I power 2 is negative. So when 12i minus I minus 11i is equal to 0i, 8 minus 6 minus 22 plus 20 is also equal to 0. So means the final answer is equal to 0. So hence we can make conclusion that 2 plus I is a root of the polynomial. Next, find a quadratic factor of this polynomial with real coefficients. Since 2 plus I is a root and the polynomial is with real coefficient, means in the polynomial we don't see any imaginary number, so means 2 minus I, the conjugate of 2 plus I, is also a root. So means we will have two complex factors. One is x minus 2 minus I, the other one is x minus 2 plus I. Now when we combine these two factors and when we simplify, we find that it is equal to x power 2 minus 4x plus 5. So this is the quadratic factor of the polynomial. Hence, solve the equation when the polynomial is equal to 0. So first we need to factorize the polynomial. Since we know that the quadratic factor of this polynomial is this one, so we can use this quadratic factor as the divisor and carry out the long division. So when we carry out the long division, then we find out that the quotient is x plus 4. Then from this long division, we can say that the polynomial is equal to the divisor times the quotient. So when we want to find the root when the polynomial is equal to 0. So we can replace the polynomial with the factors. And we know that the quadratic factor is the product of the two complex factors. So from here, we can find the first root, that is the value of x is 2 plus I. Then from here, we will get x is 2 minus I. Then from this factor, then we will get x is -4. So therefore, the solutions are 2 plus I, 2 minus I, and -4. Next example. Given that z equals 1 plus I is a root of the equation, find the values of the real numbers p and q and find the other roots. So since z equals 1 plus I is a root, and when we look at the polynomial, this is the polynomial with real coefficient where we don't see any imaginary number here. So means the conjugate, that is 1 minus I, is also a root. So from these two roots, so we will get two factors. One is z minus 1 minus I, the other one is z minus 1 plus I. So when we combine these two factors and when we simplify, then we will get this quadratic factor. After I have got the quadratic factor of this polynomial, now when I look back the question 5, I use this quadratic factor to carry out the long division. But I find that the polynomial has got two unknowns, that is p and q. If I use long division, then it is quite difficult because there are two unknowns here. So I decide not to use long division. Now I decide to use the comparing the coefficient method. So to compare the coefficient, so on the left hand side, I write down the polynomial. Then on the right hand side, I try to factorize the polynomial. So since I have got the first quadratic factor here, so means second factor is also quadratic because the polynomial is power of 4, one of the factor is power of 2, means the other factor is also power of 2. Here we don't know what is the quadratic factor here, but we can guess from the long division here. In the long division, the polynomial is power 4 and the divisor is quadratic power 2. So sure, the quotient is a quadratic power 2. So we look at the first term of the quadratic. So here I have to think, anything times z power 2, it is equal to 2z power 4. So definitely it is 2z power 2 times z power 2 equals 2z power 4. Now we go to the last number. Then I have to think what number times positive 2, it is equal to positive 2. So definitely it is positive 1 times positive 2 equals positive 2. Then the term at the middle, we do not know because there are two unknown here. So now I just put an unknown kz here. So therefore the second quadratic factor is this one. So before I can compare the coefficient, I'm going to expand these two quadratic factors. So after that, I will collect all the same terms, that is term of power of 4, term for power 3, terms for power 2, term for power 1, and constant. Now I can compare the coefficient in order to get P and Q. So when I compare for P, I find that if I want to find P, I must get the value of K first. And same thing, if I want to find Q, I must get the value of K. So therefore, I decide to find the K. To find the value of K, I use the coefficient of Z power 2. Because Z power 2, the coefficient is 7. So I compare Z power 2. So on the left hand side, Z power 2 is 7. So means 5 minus 2k is equal to 7. So from here I get k, it is equal to -1. So therefore, based on this value of k, now I can compare the coefficient for Z power 3. That is P is equal to k minus 4. Since k is -1, so P is -5. Then for Q, I need to compare the coefficient of Z. So Q is equal to 2k minus 2. Since k is -1, so means Q is equal to -4. Then now I replace back all the unknown into the polynomial. Then I get this. After we have got the values of P and Q, now we move on to the second part of the question, that is find other roots. When we want to find the roots, means the polynomial is equal to 0. Now I replace the polynomial with the quadratic factors. So for the first quadratic factor, that is the product of the two factors that we have got in the first part of the question. So from here, Z minus 1 minus I is equal to 0. So Z is equal to 1 plus I. For the second factor, from here, we will get Z is 1 minus I. Then for this quadratic factor, we find that this quadratic factor cannot be factorized. So to find the value of Z, now I use the formula. So when I substitute the value into the formula and try to simplify, so I find that Z is equal to 1 over 4 plus minus square root of 7 over 4i. So therefore, the other roots are 1 minus I, 1 over 4 plus square root of 7 over 4i, and 1 over 4 minus square root of 7 over 4i. Here, the final answer, we don't include the first root, that is 1 plus I, because the question asks for the other roots. So the root that is given in the question, that is not included in the final answer. So that's all for now. Do you understand what you learned today? If you have any question, let me know in Teacher Ailin Math Group. If you find that this video is useful, hit the like button. Don't forget to subscribe. Thank you so much for watching. I hope you keep on learning and keep on watching my videos, and I hope to see you soon. Bye.